start this video with a definition that is used a lot, not only in algebra but also in analysis. So we have three sets, x, y, and z, and two functions, f that goes from x to y, and g goes from y to z. We call the composition of g with f as g a circle f, and it's defined as g evaluated in f of x for every x in x. So if you wanted to draw a bit what this would mean, we have the set x and the function f that takes elements of x and takes them to y. Now function g takes elements of y and gives you as a result an element in z. Now the composition of g with f would be a function that does this path directly. This would be g composed with f. So let's draw some Venn diagrams to represent this definition. So I'm going to draw x, y, and z. And the dots will be some of the elements. So I can define f here. F will take an element in x and give you as a result an element in y. So I can take the first element and take it there, the second one, and let's this element will go here, and this one there. This is what f does. G can be completely different. For example, we can say this one goes there, the second one goes to the third one, and this one will go there. It's important for us to notice that these three sets don't necessarily have the same amount of elements. Set in this case has 3 elements and y and x have 4 each. So this is what f does, and this is g. Let's now think about the composition. So for the composition, what I'm gonna do is I'm gonna draw just this set x and the set z, because the composition takes an element from x and gives you a result in the last one in z. So I'm gonna do the same here. I'm gonna draw the 4 elements in x and the 3 elements in z. And what I'm gonna do is I'm gonna say how g composed with f works in here. So f takes the first element and gives you the second one here, and g takes this element and gives you the last one. So g composed with f would take the first one and do all this path to the last one. So takes the first element and gives you the last one. F takes the second one, goes to the first one, g grabs this one and goes to the second one. So this one would go as a straight line. Then the same for this one. This goes to the last one and the first one. And the last one goes to this one in the middle and then to the last one. So this one goes directly to the last element, and this is the composition. So what we do is we take an element x, we take x here, we see how f returns what this f gives us, an element of y, and then we see how g works with this element. So this is what we do, and that's the definition of the composition. Okay, so let's try and do this with an example. An example with real functions, not just Venn diagrams. So I'm going to define my function f is a function that goes from the real numbers into the real numbers, and g is also a function from real numbers to real numbers. Now these functions can go to any set. The important thing is this one and this one are the same. So f will be defined f of x equals 2 times x squared minus 18, and g of x is x minus o plus 3. So let's first talk about g composed with f in an element x. So definition of composition says that g composed with f is g evaluated in f of x. Now f of x is this definition here, so this would be g evaluated in 2x squared minus 18, so 2x squared minus 18. And let's think about this. G takes an element or a number, whatever, x, and it adds 3 to it. So now I would take this number and it would add 3 to it. So what it would do is it would say, okay, this is 2x squared, so whatever I have inside, I added 3. So 2x squared minus 18, and then would come this part, so this is plus 3. Now we can solve this. This would be 2x squared minus 15. Okay, so that's g composed with f. Now let's have a look at f composed with g, because they don't necessarily have to be the same. Oh, okay, like this. Okay, so f composed with g is the same thing, the same definition, only the other way around. So this is f evaluated in g of x. Now we know exactly what this is, and it's this definition. So f evaluated in x plus 3. And now let's think about the definition of f. So f takes something called x, it squares it, multiplies it by 2, and then subtracts 18 from it. So in this case, what it would do is it would take this, so this is x plus 3, it would square that number, multiply it by 2, and then subtract 18. And well, you can do this development in here, but it's pointless right now. If you want to do it. You just have to x plus 3 squared is x squared plus 2 times 3 times x plus 3 squared, which is 9, multiply all these by 2 and subtract 18. If you want to solve this, go ahead and do it. I'm not gonna, because it's not important, but we can notice that this and this are different, so the composition changes when we do it this way or this way. Sometimes it doesn't, sometimes it does, and well, that's where we are gonna talk about, change a bit the subject. We're still gonna talk about compositions, don't worry, but we're gonna go ahead and discuss a bit functions. Let's go to the basics. So I had a relation, let's say I had two sets, set x and set y, or two sets, and what I did was I just had a relation that was a subset of the Cartesian product x times y. And if this satisfy the property, then this could be a function. And if it were a function, then I called it f. That's what we had so far, from x to y. Now, what I can do is I can define another relation. I'm going to call it x prime, and it's going to be the set with ordered pairs yx that belong to the Cartesian product y times x. So this is the opposite, and verify that f of x equals y. Okay, so I have a function. What I do is take the relation, but instead of having xy, I'm going to have yx. Now, sometimes this relation R can be a function. Sometimes it can be, sometimes it may not. So, and that's one thing we're gonna call if R prime is a function, then we call it the inverse. I'm going to change colors because this is important. The inverse of f, and it will be noted this is not function, this is just an arrow. This is written as f minus 1. So f minus 1 takes an element y, and it will return x. And now this is very important, and we're gonna have a look at it in a theorem. A theorem that will use everything we've learned so far. So my theorem says we have a function f, that goes from x to y, and I say, well, if f is bijective, remember bijective meant injective and surjective, then the composition of the inverse of f with f gives me the identity in x, and the composition of f with its inverse gives me the identity in y. And a second part of the theorem says that if there's a g that goes from y to x, and verifies these two things, so g composed with f is the identity in x, and g composed with f composed with g is the identity in y, then f is bijective and g is the inverse of f. So let's start the proof. For this theorem we have two parts, so let's prove part 1 first. And let's start talking about the composition f inverse composed with f. Now this, by definition of composition, is f inverse evaluated in f of x. Now f of x equals y. Okay, so this is f inverse evaluated in y. Okay, where y equals f of x. But the definition of the inverse said that f inverse of y is x. That's the definition we saw earlier. So then this means that f inverse composed with f equals x, and this is the identity in x. Okay, now let's prove the second one. The second one says if there exists g such that g composed with f is the identity in x, and f composed with G is the identity in Y, then f is bijective, and the inverse is G. So we have a G. So let's define it first. Let G be a function from Y to X and verifies what my hypothesis told me. So it verifies that G composed with F equals the identity in X, and F composed with G equals the identity in Y. So what we want to prove is that F is bijective. Okay, so let's prove F is bijective. For this, we have to prove two things. So F is injective. Because f of x, let's start with the definition of injectivity. If f of x equals f of x prime, then let's use the only thing we have. Okay, we know we can compose this with G, and this would tell us G of f of x equals G of x prime. Okay, but G composed with F is the identity in X. This hypothesis right there. Oh, okay, then this tells us that this is X and this is X prime. Okay, so we had f of x equals f of x prime, and we were able to conclude that x equals x prime, so f is injective. Perfect. Now we only need the other proof, and that is f is surjective. Okay, for this, let's take y, an element in Y. We can take x equals, sorry about this, x equals G of Y. Okay, it's a definition, I define it this way. Then we can have f of x, because G is a function that goes from Y to X. So X is an element of X. And so I can apply f to it and say f of x equals f of x, G of Y. And this definition of composition is f composed with G in Y. Oh, but I said before, it was one of my hypotheses that G composed with F was the identity in Y. Okay, so this equals the identity Y evaluated in Y, which equals Y. Oh, well then, we took an element and we were able to find an element x such that f of x equals Y, then f is surjective. Oh, but because of these two things, then we have f is bijective. Well, now, okay, let's look at the theorem again. Now, the second part, it said if I have G that satisfies this, f is bijective. We've proven this, and we have to prove this other part. Okay, let's prove that the inverse of f is G. Okay, so to prove that G equals the inverse of f, we have to prove that for g of y equals f minus y minus 1 in y. This is just the definition of when two functions are the same. It's when g of y equals f inverse of y for every y in y. This is the definition we saw in the last video, so if you don't remember, I suggest you go back and look at it again. But what is g of y? Well, g of y equals g of f of x. So g of y equals g composed with f in x, and this equals x, and x equals the inverse of f in y. Oh, but this is valid for every y in y. We didn't take in particular y equals 1. No, we just took an element y in y and proved that g of y equals f inverse in y. Oh, then we have that f inverse equals g. And this is where I'm gonna leave this video, but I suggest you practice, you check these proofs again, and in the next video we'll do a few